Okay, let's jump right into this explainer. Today, we're exploring a completely groundbreaking way to think about one of nature's absolute most unpredictable events, earthquakes. You know, for decades, scientists have been trying to figure out exactly where and when the ground is going to shake. But as you probably know, it remains a massive, massive challenge. So today, we're looking at a brand new falsifiable hypothesis that totally changes the game on how we forecast earthquake locations. Here's our agenda for today. We'll go from the core earthquake prediction problem to a new seismic hypothesis, then the 5 warning signs, testing the theory, how to prove it wrong, and finally, the real-world impact. Let's get into it. Section 1, the earthquake prediction problem. To really grasp this, we first need to understand why figuring out exactly when the ground will shake is so incredibly tough. Right now, we're actually pretty good at knowing where fault lines are, right? We know where tectonic pressure is building up over time. But here's the kicker. Just knowing there's pressure building on a locked fault doesn't actually tell us when it's going to finally snap. It's kind of like knowing a balloon is totally full of air, but you have no idea which specific breath is going to pop it. The missing piece? Knowing if that pressure has anywhere else left to go. Because, you see, high strain alone doesn't actually determine when or where a fault will rupture. In the real world, heavily locked faults can just sit there, silently, for literally decades without moving an inch. And on the flip side, you might see these ordinary earthquake swarms that seem super scary at first, but they just fizzle out without causing a major disaster. The big takeaway here? Strain is only part of the story. Which brings us to Section 2, a new seismic hypothesis. This introduces a fascinating new proposal designed to solve this exact problem. It comes from a recent paper by Kevin L. Brown, who is a researcher, inventor, and author. He introduces what he calls the boundary closure seismic localization hypothesis. And what Brown suggests here is that we should basically stop just looking at the pressure and start treating tectonic plates a bit like a giant traffic network. The core idea here is boundary closure. Now, the scientific definition is a little heavy. It's the progressive reduction of lower energy ways a tectonic system can handle continued deformation. But let's break that down into plain English. Think of it like a massive traffic jam. Imagine a busy highway where cars, which represent tectonic pressure in this case, just keep flowing in. Normally, some of those cars can take exit ramps to relieve the traffic. But what if those exit ramps are slowly being blocked off? The cars keep coming, the ways out vanish, and eventually, the pressure has to release in a huge crash. That is the beating heart of this hypothesis. Moving right along to Section 3, the 5 warning signs. Brown's framework actually breaks this impending crash down into 5 distinct measurable warning signs. An earthquake happens when these complex geological events occur, but we can easily translate them into simple terms. First, we have deformation gradient concentration. That simply means building pressure. Second is structural constraint. Think of that as the bottleneck in the rock. Third, redistribution insufficiency, meaning there are absolutely no alternative escape routes. Fourth is closure rate, so exactly how fast are those exits closing? And fifth, rupture viability, which just asks, is this fault even large enough to snap in a massive quake? So the absolutely crucial thing to remember here is what Brown calls the multiplication rule. Basically, a bottleneck alone won't cause a massive quake, and a random pressure spike alone isn't enough either. No single factor does it on its own. All 5 of these warning signs have to converge at the exact same time and place. If even one is missing, like, say, the pressure actually finds an open exit ramp and safely escapes, then the major earthquake just doesn't happen. All right, Section 4, testing the theory. Now you know and I know that an idea is only as good as its proof. You can't just have a cool theory. You have to be able to test it. So how do we actually validate this in the real world? Well, the research starts by looking backward. The model examines the structures of huge historical quakes from the past decade, like Tohoku in 2011 or the Noto Peninsula in 2024. This looks at how strain reorganized and literally closed off exit ramps right before those massive ruptures actually happened. But to be totally clear, just looking at the past isn't enough to prove anything. The real test requires looking forward. The validation mechanisms for this hypothesis involve running 180-day perspective forecasts. That basically means scientists make a prediction for the next 6 months and then wait to see what happens. They compare the target danger zones to normal regional baselines. They use some pretty complex math to measure things like spatial entropy, which is honestly just a fancy way of saying how scattered the pressure is. And they track if the fault pathways are shrinking in real time. And this builds into something super clever called the ablation test. Step 1. You run the full forecasting model with all 5 variables.
Step 2, you deliberately pull out Brown's new variables, the ones measuring those closing exits. Step 3, you check the results. If the forecast gets noticeably worse without those variables, well, it proves that measuring the closing exits really is the secret sauce, making the predictions accurate.
Next up is Section 5, how to prove it wrong. Validation is great, but in science, a strong hypothesis absolutely must be falsifiable. That means it has to lay out the exact rules for how it could be proven completely wrong. A true scientific method actively invites failure to ensure rigorous truth. And Kevin L. Brown's paper doesn't shy away from this at all. It's exceptionally clear about its falsification parameters. It lays out precise, strict conditions where the entire hypothesis should just be totally rejected by the scientific community. So, what would actually prove this theory wrong? Well, it completely fails if the high-scoring, high-danger fault segments don't actually produce more quakes than our standard old models. It fails if taking out the escape route variables doesn't hurt the forecast's accuracy. It also fails if we see these so-called warning signs happening all the time during boring, quiet periods where no quakes happen. Basically, if simpler models perform just as well or better, the whole theory falls apart. But you know what? That strictness is exactly what makes it good science. And that brings us to our final section, Section 6. Real-world impact. Let's talk about how all this math and theory translates into real-world applications for us. The biggest implication here is being able to tell the difference between a false alarm and a true threat. By distinguishing between a dangerous bottleneck where exits are actively closing and stress is localizing, and a fault that is safely redistributing its stress through harmless slow slipping, scientists can actually avoid unnecessary panic. It helps us know if a buzzing fault is just safely letting off steam or if it's genuinely preparing to snap. Now, I need to make something absolutely clear. This is experimental science. As the author states, this method does not replace official hazard maps, building codes, or your local emergency warnings. The research is incredibly promising, for sure, but you should always follow your local emergency management guidance to stay safe. So this leaves us with a profound question to wrap up our explainer today. If we can finally measure how fast Earth's geological exit ramps are closing, if we can see these traffic jams building in real time, are we on the verge of finally solving the earthquake prediction puzzle? It's a thrilling possibility, and one that scientists will definitely be testing rigorously in the years to come.